Hello and welcome to my YouTube channel. Today we'll be talking about transistors. This is chapter 2 of Applied Electronics. Okay. So when it comes to transistors, right, as the name implies, it means the transfer of signals across a resistor, right? And the reason why we tend to do this because we want to increase or amplify a weak signal. So transistors are mainly used for amplification of weak signals. So if I have a very strong signal and it's very weak, for example, you can think about sound, right? Imagine you are having a microphone and you want to increase the voice that is coming from a speaker so that everybody in the room can hear the person very well. So within that microphone, you have transistors there, and these transistors amplify the sound so that everyone can hear. So now, how do we get transistors, right? So the commonly used transistors that we have, right? We have about three commonly used transistors. We have union junction. We have bipolar junction. Then we have, I think we have four in general. We have FET, right? Field effect transistors. Then we have MOSFET as well. So we have four commonly used transistors. So, but today our focus is going to be on bipolar junction transistors. And when it comes to bipolar junction transistors, they are formed by joining two p-n junctions in series. We already talked about p-n junction in the previous video. So if you want to understand p-n junction, you can pause and go and watch that video. Right? So you combine two p-n junction, and in doing so, you can create two kind of bipolar junction transistors. We have PNP and an NPN bipolar junction transistors, right? So with each of these bipolar junction transistors, we have three terminals, right? That are associated with each of them. Each of them is going to have an emitter terminal. Then we have the base terminal and then the collector terminal. All right. So a bipolar junction has three terminals, and they are the collector, base terminal, and one emitter terminal. Now, within each of these bipolar junction transistors as well, they also have two junctions. So we have the emitter base junction. So the emitter base junction is going to be the junction that adjoins the emitter terminal, right? So we have it here, J1. And when it comes to the collector base terminal, a collector base junction is going to be the junction that adjoins the collector terminal and then run J2. Now, why are these junctions important? Because these junctions are very crucial, right? They become crucial when it comes to trying to create or trying to ensure that we can pass current through the bipolar junction transistor. If we are trying to make sure that the bipolar junction transistor conducts current, then these junctions become very important, right? So from here, we talk about one of bipolar junction, one of the bipolar junction transistor, which is PLP, and we talk about its transistor action. What that means is that we are trying to see how NPN bipolar junction transistor is going to conduct current. It's going to allow current to pass through it, right? And when it comes to doing that, first of all, if we are giving NPN, right? We are giving an NPN bipolar junction transistor. What you can realize is that you can see that it's going to have three readings, right? we have called the terminal region, the base region, and then the collector region. And when it comes to the emitter region, we tend to have majority electrons. So as the name, you can see here, N stands for the fact that we are having majority electrons. So negative, N is from what? Refer to negative charge, and the fact that we are dealing with electrons tend to have negative charge. So that is what the emitter region, we have majority electrons. And when it comes to the base, where we have the majority holes, and then the collector region, we have majority electrons as well. Now, in order for current to pass through NPN bipolar junction transistor, what we do is that we make sure that the emitter-based junction is forward bias, which means we connect the positive terminal of a voltage source to the base region or base terminal, because the base, we have majority holes there, right? We have majority holes, the base, so meaning we have positive charges there. Now, when it comes to the negative terminal, you connect it to the what? To the emitter terminal. And then before it goes into the emitter terminal, it passes through an emitter resistor, right? This is a emitter resistor that we have. Now, that is how you connect the emitter-based junction and forward bias, all right? Now, when it comes to the collector-based junction, that is rather connected in reverse bias, right? So that part of the junction is reverse bias, which means we connect the positive terminal of a voltage source to the collector region where we have majority electrons, and then the negative terminal to the P region or the base region where we have majority holes, right? So that's the first step. Now, once this has taken place, what is going to happen is that we now have a situation, right? Because we have majority electrons in the emitter region, right? And then majority holes in that base region there. And with the base being connected to the positive terminal, right? Because of the positive terminal that we have, where we have positive charges, right? We have a lot of positive charges there. And due to the force of attraction, because if you have positive and negative charges, we know that they are going to attract each other. So due to the force of attraction, the majority electrons in the emitter region are going to force their way to move to the positive terminal of the voltage source, which is connected to the base region where we have majority holes, right? So you have movement of electrons into the base region, right? And these electrons will force their way to come to the positive terminal that we have over here, right? Now, and bear in mind, when it comes to the base region, you can see that compared to the other two regions, it's narrow, right? Right? Is the narrowest. So what that means is that when it comes to the way that region is being doped, we make sure that it is lightly doped, right? That means we ensure that the amount of majority holes that we have here, they tend to be less, right? Though holes are very bad, the majority is not that much. Then, in doing so, when electrons move from the emitter region into the base region, we have a combination of holes, then leaving more electrons. Because the base region is lightly doped, that means electrons will move in there, recombine with what the existing holes there, but there's still going to be an inflow of electrons that continues to take place. So now you have a situation whereby you have more electrons that are there, but those electrons have already entered that has recombined with what the existing holes there. Now there's no more any holes to be combined. So you have now more electrons in the base region. And these electrons in the base regions are forward biased to the positive terminal, which is connected to the collector terminal. Right. So they force their way and then come to the pole, the positive terminal that is connected to the collector terminal. And in that process, you have large amount of electrons, right, moving into the collector region, and then from there, they migrate through the positive terminal that is connected to the collector terminal. Right. So you have large flow. So as a result of this, you have the flow of current. So you can see that when it comes to we define current as a flow of electrons. So the movement of these electrons constitute current. And when it comes to the direction of current, the direction of current is opposite the direction of flow of electrons. So if you have electrons are moving this direction, meaning the current direction will be opposite in that very direction. So in ordering, we have this, as you can see there, you can see electrons are moving right from the N region into the P region, and then come to the positive terminal that is connected to the base terminal. So we have electrons moving that direction. So that means the flow of current is going to be the opposite. So we refer to that current as the base current. Now you also have electrons moving into the collector region. From there, they force their way to the positive terminal, which is connected to the collector terminal. And that current is also going to be opposite to the flow of electrons. So we have collector current, referred to as collector current, moving in the opposite direction. Then we come to the emitter current. The emitter current, right, is going to also be opposite the flow of electrons. So the emitter current is going to move the opposite direction. And in that process, we can now have three big currents, right? We have the emitter current, base current, and then the collector current. And if you were to apply Kirchhoff's current law to this diagram, you realize that the base current and the collector current are entering while the emitter current is leaving. All right. So in that process, we have the emitter current being equal to the sum of the base current and then the collector current. And this is how current is going to pass through the transistor. Now we are going to be talking about the next action, transistor action, which is going to PLP, bipolar junction action. See you in the next video. Bye-bye.